set to track. So what we do is we look through the array, have a set which tracks, which stores all the values that we've seen so far, and if we come across a value that's already in the set, we can do, return false, otherwise at the end we return true. Sets give us constant time lookup. We're going to create a set called C. There's a 4 times the numbers, then C, return false. Oh, sorry. We have to return true if it's duplicate, and return false.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve contains duplicate. This is another problem from the blind 75 list of questions we've been working on. So I like this problem because it's a good problem for beginners, but there's also multiple solutions to it that I'd like to go over in this video. So we're given an array of numbers. We want to return true if there's any value in that list of numbers that appears at least twice, but maybe it could appear 3 times or 4 times, right? Just at least twice. And we want to return false if there aren't any values that appear at least twice. Basically what that means is that every value in the array is distinct. So let's take a look at an example. We have 1, 2, 3, and then we have 1 again. So of course this has duplicates, right? So we return true, and the easiest way we would be able to detect that is by brute forcing this. So given these numbers, the first thing we do is look at the first number. It's 1. How do we know if this is a duplicate or not? Well, we'd have to compare it to every single number in the rest of the array. So that would be a big O of n time operation just to check if the first number is a duplicate or not. And then we'd have to do that for every number. Then we have to check, is the second number a duplicate? How do we know? We have to compare it to every other number. We do the same thing with the third one and the last one. And so since we're doing it for every number in the array, the overall time complexity is going to become n squared. And by the way, in this case, n is just the size of the input array. So the brute force solution is big O n squared time complexity, but the good thing is we don't need any extra memory, so the memory complexity is big O of 1. It's definitely not a bad solution, but the question is, can we do better than that? And yes, we definitely can. A second approach that will help us is sorting. What happens if we took this array and we sorted it? It would look a little bit different. It would look like this. Okay, but how does sorting help us? Well, let's think about it. If we sort the input, then any duplicates that do exist in the array, and clearly we see that 2 duplicates exist at the beginning of the array, they're going to be adjacent. So when we're trying to detect any duplicates in here, we only have to iterate through the array once. And as we do that, we're just going to be comparing 2 neighbors in the array, checking if they're duplicates. Next, we're going to shift our pointers to the next spot. Are these duplicates? Are these duplicates? Etc., etc., until we've finished the entire array. In this case, we see that these 2 adjacent values are duplicates, so we can return true. And what's the time complexity of this? Well, the one pass is just going to be big O of n, but we know that sorting does take extra memory, or not extra memory, it does take extra time complexity, and that time complexity is n log n. So that's the bottleneck in this solution. But again, we don't need extra space if you don't count the space that's used by the sorting algorithm. So in this case, we do have a slightly better solution than brute force. But actually, if we use a little bit extra memory, and it's really a trade-off, if we sacrifice space complexity, we can actually achieve better memory complexity, and let me show you how. So suppose we don't sort our input, we're given the default input, but we use extra memory. We use a hash set But what exactly is a hash set going to do for us? It's going to allow us to insert elements into the hash set in big O of one time. But it's also going to allow us to check. We can ask our hash map, does a certain value exist? We want to know, does this 1 exist in the hash map? Well, if we start at the beginning of the array, so far nothing is in our hash map, so a 1 does not exist in our hash map. That means this 1 is not a duplicate. You can see that this is an improvement over the brute force. Previously, to determine if this was a duplicate, we had to check every other value in the array. This time we don't. But after we have checked if this is a duplicate, we do have to add it to our hash set, because later on, if we encounter a 1, like over here, then we determine that this is a duplicate because we know that there's already a 1 in our hash set. So next we're going to check 2. 2 is not a duplicate. Add it here. Is 3 a duplicate? Nope. Add it here. 1. Is this a duplicate? Yep, there's a 1 over here. So we return true. This does contain duplicates. And by the way, since each operation was just big O of 1, we had to do that for every value in the input array, and we only had to scan through the list of inputs once. The time complexity is going to be big O of n, but the space complexity, we did have to sacrifice a little bit. We have to create a hash set, and the memory that hash set will use could be up to the size of the input array, which is n, so we do end up using extra memory. But that's not too bad. This is about as efficient as we can get in terms of time complexity. So let's get into the code now. Okay, so now let's get into the code. So the first thing I'm going to do is create that hash set. In Python, you can do that just like this. It's just called a set. And then the simple thing is just going through every value in the input array nums, and before we end up adding it to our hash set, because remember, we want to add every one of these values to our hash set just like this. But before we even do that, we want to know, is n a duplicate? Does this value already exist in our hash set? And if it does, we know that our array contains duplicates. So we don't even have to continue through the rest of the array. We can immediately return true because we found a duplicate. But if it doesn't contain a duplicate, we're going to add that value, then iterate through the rest of the array of nums, and then the loop will exit, and then we can return false to indicate that we did not find any duplicates in the array. Now let's run the code to make sure that it works. And on the left, you can see that yes, it does work, and it is about as efficient as we can get. So
okay, so I guess for this question, there's 2 ways to do it. First is, you can store your list, and then you compare the I and the I minus 1 element to see if it's equal. If it is, you return true. That means that element has been seen. Problem with this is the time complexity is n-log n, but the space complexity is constant. And if you have a trade-off for space versus time, you can use this set approach where you have a set and you keep adding elements. You loop through the nums and you add elements as you loop through nums in the set. And when you come across an element that's in your set, then you return true. Otherwise, at the very end, you return false. Set gives us a constant time lookup. So the time complexity is O of 1, and the space complexity is O of n, where n is the length of nums. Okay. Let's go to the next question. Now the anagram. Give it 2 strings s and t. Return true if the 2 strings are anagrams of each other. Otherwise, return false. Okay, so an anagram is a string that contains the exact same characters as another string, but the order of the characters can be different. Okay, so if we have 2 strings and we want to see if they are anagrams of each other, how can we do it? Well, the character count the count of each character in both strings must be the same for it to be an anagram. So let's see, you can, for the first string, create a dictionary maybe you can use, because dictionaries can help us keep track of counts and give us, and these 2 strings consist of lowercase English letters only, okay? They're only lowercase. So we have a dictionary where we store the count of the first string, each character in the first string, sorry. And then we go to the second one, and we store the count of each string. Okay? And then we compare their counts to see if it's equal. So yes, first I would create two dictionaries called count underscore s and count underscore t, which will keep track of the counts of each character in each string. So for car in s, if s in car, sorry, if yeah, so okay, so we do the same thing with string t, the second string. Okay, now what we do is we just compare their counts. So when we compare counts, we want to compare both ways. So we want to compare every character in S with every character in T, and then every character in T with every character in S. For example, if you have character S has like two letters, like J and two characters, J and A, and string T has J A M. So every character count of the characters in S is equal to the one in T, but T also has one extra character, so we have to compare it both ways. So for key, and I guess we could even create a method here that compare, which takes two dictionaries, dictionary 1 and dictionary 2. For key in DC, dictionary 1, if key not in DC, false. Okay. If key not in there, or C2 key, C1 key, return false, true. Okay. So all we now do is return this. So yeah, that should take care of it. It's not a dictionary 2, or if it's in there, dictionary 2 is not equal to dictionary 2. Okay, yeah, that does it. Let's look at the solution that they have.
Hey everyone, welcome.
I always find that watching the solution videos is good because sometimes they can have an approach that you didn't think of, and it's always good to have different approaches for one question. But that just means that you get more tools in your toolbox when you're trying to solve questions.
Welcome back, and let's write some more LeetCode today. So today let's solve the problem valid anagram. And we're actually going to be solving this a few different ways, so maybe you will learn something today. So we're given two strings, S and T, and we want to return true if T is an anagram of S, or basically if both of the strings are anagrams of each other, and false if they're not anagrams. So main thing that they don't mention in this problem is what exactly is an anagram. And basically, it means that, to call T an anagram of S is basically saying that using the characters of S, all of the characters, right, every single character, we can create the string T. So basically, they're made up of the exact same list of characters. So the string S, you can see that it has 3 A characters, 1 N character, 1 G character, 1 R character, and 1 M character. So it's made up of, in total, 7 characters. So that must mean that if T is an anagram of S, T has to have exactly 7 characters as well, which clearly it does have 7 characters, but are they the exact same characters as I wrote up above? Well, let's check. Okay, does it have 3 A characters? 1, 2, 3. Yep, it has 3 A characters. Does it have a single N character? Yep, it has exactly 1 N character. Does it have a G character? Yes, exactly 1 G character. Does it have an R? Exactly 1 R. It has exactly 1 M as well. So it has the exact same characters and the same quantity of each character. That's also important, right? Because 3 A's have to exist in T as well. So in this case, they're anagrams. We can return true. That's great. Second example, rat and car. Both of them have an R. Both of them have an A character, but one of them has a T while the other has a C character. They're both the same length. They're both length 3, but they have one differing character, so they're not anagrams. We return false in this case. So the first solution I wanted to talk about is probably the most obvious one, and probably by just listening to me talk about anagrams, you might be able to come up with this by yourself. We just want to count the occurrences of each character in both strings, right? What's the easiest way to do that? Well, you could use an array or a hash map. That's what I'm going to use. I like hash maps. Basically, what the hash map is going to look like. So basically, we're going to have 2 hash maps, one for each string, and the key value in the hash map is going to be the character. So for example, A in string S, right? Let's use a different color. So A in string S. So how many A's are there? There's 3 A's, right? The value is going to be the count. The key is just going to be the character. We're going to do that for every single character in the string. So that's A, N has 1, G has 1, R has 1, and M also has 1. And we know that T is the exact same, right? It has 3 A's, 1 N, etc., right? I could continue this. So in the end, you can see that they're the exact same hash map, right? And once we've built these hash maps, we can then go through the keys and then compare that the counts for each character are the exact same, which in this case, yes, it is. So then after that comparison, then we know that they're anagrams, then we can return true. And how exactly I'm going to do that is I'm just going to actually iterate through the keys of one of these. So in this case, for example, I'm just going to iterate through all the keys in string S. So A, N, G, and then make sure the counts, right? We want to make sure that the count of each of the characters is the exact same. And if we make sure that both strings have the exact same length, before we actually do the hash map stuff, then we actually only have to iterate through one of the hash maps and comparing it to the other hash map, right? Because if we make sure that T has exactly 3 A's, T has exactly 1 N, T has exactly 1 G, etc. If we make sure that all of that is true and that's inside of T, then we pretty much know T is exactly the same as S because they have to be if they are the same length. So that's the solution. Time complexity of this is big O of N, or rather, let's say big O of S plus T, because we're going to have to iterate through both of the strings. So so that's the time complexity. The memory complexity is the same, S plus T, because clearly we are building hash maps that are going to be of size, potentially up to the size of S and the size of T. So the downside of this solution is we are going to need some extra memory, and the second solution that I show you is actually going to solve that memory problem. So stay tuned in the video if you want to see that. But for now, let's jump into the coding solution.
So if you compare the lengths in the beginning of the 2 strings to check if they're anagrams, if the length is not the same, you just return false. Well, let's say the length is same, then you just have to, when you compare the 2 hash sets or dictionaries, you only have to loop through it once, because the lengths are the same, right? And all you do is you just check if, when you're comparing the hash sets or dictionaries, you check if a key in one of them is not in the other, and if it is, check if the count is the same or not. So I think, and then that should take care of it. Yeah, I think that works.
Hey everyone, counting the occurrences. Like I mentioned, a main thing we're just going to be doing is counting the characters in both of the strings. So we're going to create hash maps for that. This is how you can do that in Python.
So also, I didn't know this, that in Python you could take a dictionary, do like dot get, and then put the key in there, and then you can also put a default value, so you don't have to like check if some key is in the dictionary. So then that saves you, a whole bunch of lines. I guess there's solution number 2. Let's see what solution number 2 is, because for this one, the time complexity is O of n, and space complexity is O of n, when n is the length of, s and t when they're saying, if they're saying. Yeah, and also, you can just compare dictionaries by just equating them. So like, if you have two dictionaries called, count s and count t, you can just do like count s equal count t, and it does a comparison for it, instead of you, looping through each, or writing, like the for loop to loop through each key. So I don't know, you can do that. But let's look.
Hey
at
everyone, welcome to function.
Is, that they said it has constant time complexity, I think, yeah.
If you took all these characters and put them in a hash map where we can count the occurrences, then it's pretty easy to check if they're equal. But isn't there another way? What if we made sure that the characters show up in the exact same order every single time? What do we mean by order? Well, one possible way would be sorted order, right? Because if they really are the exact same characters, then if we put them in sorted order, then they should actually become the exact same string. Then we can literally just do an equals operation on both of the sorted strings and guarantee that they're going to be equal. But the downside is, what's the time complexity of doing sort? Well, in some cases, with bad sorting algorithms like bubble sort or something, it might be n squared, right? Good sorting algorithms can do it in n log n time, right? Worst case, big O of n log n time. But the space complexity is kind of iffy. Usually sorting algorithms, at least good ones, actually do use extra memory. They use O of n extra memory, but sometimes they don't. Sometimes they can be really optimized and actually run on constant extra memory. It will depend on which built-in library function you're using, but usually for some reason interviewers just assume that sorting doesn't take extra space, so it's definitely something to discuss with your interviewer. Yeah, so basically if you just sort it, it solves the problem for you, right? Because if we took anagram and we sorted it, we'd get AAA, G, M, N, R, right? It would be the same order. And then if we take this string T, sort it, it's the exact same characters, so when we sort it, it should be the exact same string, and it is. So now let's get into the code of this solution. Okay, so now you can see that these were the two solutions we originally came up with. Now let's do the third and final solution. We can just run the sort function on S and the sort function, the built-in sort functions at least, in Python on T as well. And if they're exactly equal, it'll return true. If they're not equal, it will return false. Let's run it to make sure that it works. And on the left, you can see, yes, it does. It's relatively efficient. But technically, it's not as efficient as the two previous solutions that we came up with below. And who knows, maybe your interviewer will actually want you to write out your own sorting function for this. But I really hope that this was helpful.
I guess anytime you want to have constant space complexity, sort is kind of the approach to go, sorting a list or sorting a string. But like, I know that lists have a built-in sort, but in Python, if you use sorted for sorting strings, that returns a list. So you're still using constant space, or you're still using some kind of space for it. And yeah, I think also like some sorting algorithms require you to Python, the dot sort requires a string additional space for merging sorted blocks. So, okay, yeah. So I guess you do need space complexity of O of n. There's one more approach I think here. Let's talk about hash optimal. Oh, interesting. One nice way of doing it is you get the ASCII value of the character that you look at, that you're seeing, right? And so you have two anagrams, two strings, right? So you go through the first, loop through the first one, and you you find the ASCII value of it. Sorry, not ASCII value, the number in the alphabet. Like for example, A is 1, or A is 0, B is 1, and so on and so forth. And you put that, you know, in an array, in an array of 26 elements. And yeah, so what you would do is you would have an array which has 26 elements. You loop through the first string. You would add one every to each index when you see you know, a character. Like for example, if you see yeah, so if you see the, you know, letter A, the 0th element in the array would increase by 1. And then when you look at the second string, anytime you see, you do the same thing except you put -1 from it. And then at the very end, you would loop through this array, and then you would check if the values are 0 or not. So essentially what you're going to do is first you have to, in this one also you want to, do I need to check if the values are same first? Okay, if they're not same, I can just return false. And then yeah, so essentially what you're going to do is first you check if the length of S is not equal to length of T, where, you know, these are the two strings you're, you know, trying to check if they're anagrams of each other. Return false. So what you first next do is you do, okay, you would create an array of 26 elements, and each element in the beginning will be 0. These will correspond to the indices, for example, indices of, like, you know, the alphabet. So the first element in this array would be correspond to, you know, the letter A. And then for I in range of length of S, now we can just do one loop through S, because now we know that the length of S and T are same. All we do is we take ord of S of I minus ord of A plus equal to 1. And then we take ord of T of I minus ord of A, and then we do minus equal to 1. Then what we do is for val in count, if val is not equal to 0. Again, for this one, the space complexity would be O of 1, because your array will always have 26 elements. It doesn't vary with the length of your thing, your array. It doesn't vary with the length of the two strings. And time complexity will just be order of n plus m when, you know, they're equal. Otherwise, if they're not equal, they'll just be false. This is an interesting question. I guess they're you know, in this case, if you want to have constant complexity, you don't need to use some kind of sorting. All you have is, you know, an array that has 26 elements, where each element, or each element in the array corresponds to how many times you see a character. And then at the end, you just check to see if, you know, each value in the array is equal to 0, right? That means it was seen in equal amount of times in both S and T. So this is a pretty cool approach to give you constant space complexity, but still linear time complexity, which is fine. Okay, so I'm gonna grab a, actually I'm gonna warm it says all systems are operational.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem concatenation of array.
Also, I just realized my audio capture file was down. Okay, so I was just looking at it, and you guys probably didn't hear the question. So the question is concatenation of an array. So you're given an array, integer array nums of length n, and you want to create a concatenation of that array. So if you have an array of elements 1, 2, 3, you want to return an array of 1, 2, 3, 1, 2, 3. So it'll be twice as large. And the approach I thought was that we just have 2 for loops, and then loop through nums 2 times, and each time add the element of nums in your upper array, and then you just return the output.
Given an integer array nums of length n, so maybe something like this, where the length is obviously 3 values, we want to return a concatenation of this array, meaning we take this array and then append it to itself. So then the output array would be the original array plus the array again. So basically adding each of these values to the end of the array. So 1, 2, 1. So we have 2 copies of this array combined into a single array, and that's what we want to return. Now, there are many ways to solve this problem. The easiest way probably would be to just iterate through every value in the input array. So go here, 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 and then take each of those values and just append it to the original array. So we can take the input array and then use that as the result and then return that. So we would take the first 1, add it to the end, take 2, add it to the end, take 1, and add it to the end. There you go. There's the array, and that's what we would return. Another approach would be to actually create an output array. Initially, it would be empty. I'm just drawing it this way because I know this is how much space it's going to take. But initially, it would be empty. We take each value and append it to the array. So 1, 2, 1. And in this case, we want a concatenation. So we would do this once, and then we'd do it twice. So now we'd add 1, 2, 1. If this problem was not asking for a concatenation and it was actually asking for maybe 3 concatenations, then we would just do this same operation another time. So this is kind of a more extensible way to solve this problem, because we might want to concatenate a variable number of times. And the important thing to note is that since this is like a dynamic array and we're taking each value and just pushing it to the end, each time we push a value, it's going to be O of 1 time. And we're going to do so n plus n times, because the input array is of size n, and we're basically creating a concatenation of it. So we're doing that with this array twice, but that's still going to be big O of n. That's why I think doing it this way isn't really bad, because the time complexity is the same. We are technically needing extra memory complexity if you count the result as needing additional memory. If you don't count it, I guess we're doing this in constant memory. But now let's go ahead and code up this approach. Okay, so we're going to create our result. I'm going to call it ans for answer. Maybe there's a second variable given called x, or some.
greatest element on right side. Given an array R or R, replace every element in that array with the greatest element among the elements to its right, and replace the last element with this one. So you want to replace every element with the greatest element on its right side. So an approach that I think about is that I have to keep track of the maximum element to the right of an element, right? And I have to go from right to left. So that's what I'll be doing. So I'll move from the very right to the very left. And each time, as I loop through, I'll keep track of the maximum element that I have, and then I'll update the final array. I mean, the output, so I have to return output array, right? So let me first do, so array's length is minimum 1, and so let's create an index element called idx index variable, which is going to be length of array minus 1. While index is greater than 0, we're going to keep moving. And let's also create a variable called max val, which is going to equal to the last element of the array. And then let's also actual index will start at length of array minus 2. And so we'll also do is we'll create an output array. Oh, we need to put this. Yeah, actually we can even just return the original list. So while index is more than 0, is greater than 0, all we do is we go temp is equal to array index, and then we do is we go array index will equal to max val, and then we update the max val to the maximum, right? And then we update the return array. Let's see if this works. Oh, anytime you do like a while loop, you should always update your index, otherwise it will just run forever. This doesn't work. Well, index is more than 0, so. Oh wait, you have to. Right, so what you do is you go. Minus 1, okay. And then you go here. Oh, well, index is greater than or equal to 0, sorry, not greater than, so yeah. Submit. Okay, yeah, it worked. So in terms of time complexity, it's O of n, where n is the length of the array, and space complexity is constant, because I'm not creating a new array. Let's look at the solution that they have.
Let's solve LeetCode 1299, replace elements with the greatest element on the right side. So we're given an array, and we want to take each element in the array, for example 17, and replace it with the greatest element on the right side of it. So we scan through 18, 5, 4, 6, and 1. The greatest one is 18, so we can replace 17 with 18. The last element, 1, doesn't have any values that come after it, and the problem wants us to replace it with a negative 1. So basically what I do is just consider that there's an imaginary negative 1 over here that's not a part of the array, but we're just going to replace 1 with this negative 1. Now, if you don't know how to solve the problem, the first thing you want to do is draw a picture. This is going to make it a lot easier for you to visualize it and notice patterns. So once you've drawn the picture, choose the easiest way to solve the problem first. So we already kind of did that. So to replace 17, we're going to look at every element that comes after it. So each of the 5 elements, and we're going to take the maximum of these 5 elements. And we see that 18 is the max, so we replace 17 with 18. We can repeat this process. So for 18, we look at the last 4 elements. we see that the max is 6. So we can replace 18 with 6. To replace 5, we look at the last 3 elements. Again, the max is 6, so we replace 5 with 6. To replace 4, we only look at the last 2 elements. Again, the max is 6. To replace 6, we only have to look at the last element, which is 1, so we can replace 6 with 1. And of course, 1 is going to be replaced with -1. Once you draw it out, it's pretty easy to recognize the repeated work that we're doing. Because of the repeated work, this solution runs in O of n squared time. It's also obvious that since we're doing a lot of repeated work, that there is a better solution. So let's try to analyze it to come up with a pattern that we can use to make it more efficient. So the first thing that I notice is that the new value in position 0 is equal to the maximum of each value that comes after it. So in the array from position 1 to position 5. To get the new value in position 1, we did something very similar. We scanned through each of the last 4 elements. So we took the max of the array from position 2 to position 5. So this makes it even easier to recognize the repeated work that we're doing. We're taking the max in the array from 1 to 5, and then we're doing the max again from 2 to 5. Wouldn't it be easier for us if we took the max from 2 to 5 first and then stored that value, and then to get the max or to get the new value in position 0, all we have to do is take that stored value and compare it with the original value in the array in position 1. Let me draw it out to make it even easier. So the thing to notice is that these two equations that we wrote to get the new value in position 0, they're both equivalent. But in the original value over here, we have to get the maximum of 5 different values. Over here, in the new one we wrote, we only have to compare 2 values to get the maximum. This cuts down on all the repeated work. So the hint here is that to get the new value in position 0, we have to first get the new value in position 1. And to get the new value in position 1, we have to get the new value in position 2 first. So this problem leads us to iterate through the array in reverse order to cut down on the repeated work. So we're going to start at the end of the array and then compute the new values in reverse order. Of course, the new value in the last position is simply going to be -1 because that's like our base case. Okay, so let's go through it in reverse order. So our max value initially up until this point, before we've even gone through the array, is just -1, right? That's our base case. So we're going to replace 1 with -1. Now we want to recompute the maximum, right? And we only have to look at 2 values to do it. We only have to look at +1 and -1. So our recomputing the max up until this point is going to be +1. So we can replace 6 with +1. Now we're going to recompute the maximum again, and all we have to do is look at 6 and 1. The 6 is greater, so 6 is our new maximum. We can replace 4 with 6. Now we're going to just keep repeating this, right? So our new maximum up until this point is 6 because 6 is greater than 4. We just have to look at 2 elements. So we can replace 5 with 6. Now we're going to do it again. The max can be set to compute the maximum, right? But we're new max that we just compute array itself. So we can do that. And of course, let's submit it and see that.
Yeah, it's the same approach like that, where you start at the very right side of the array, and then you go backwards, and then you keep updating your maximum values. Yeah. Actually, let me add a window capture. So you guys can see, what I'm typing and whatnot. Put that right here.
Like a pen or a brush, AI is only a tool.
So don't brag like a pro if you grunt like a fool.
Looking to work with actual pros? Hire experts on Fiverr who get the job done.
Let's go to the next question. We don't do dark mode. I do dark mode here. Here it is. And then that's a little more easier on the eyes. Okay, so let's go look at this. Let's look at this question. This subsequence. Given two strings S and T, return true if S is a subsequence of T, or false otherwise. Okay. A subsequence of a string is a new string that is formed from the original string by deleting some. A subsequence of a string is a new string that is formed from the original by deleting some of the characters without disturbing the relative positions of the remaining ones. So A is a subsequence of A, B, C, D, E, while A, E, C is not. Okay, so you want to return true if S is a subsequence of T, otherwise false, okay? So we need to somehow keep track of the overturning of the characters. Okay, so let's see. So one way we can do it is have 2 pointers, one for S, one for T. So we start in the beginning of T and the beginning of S. If they're both the same, we move the pointer of S to the right. We do the same thing with the pointer of T. So now we're comparing the second element, second index of each element, of each string. If they're not the same, we just move the index of T, and we keep doing that. Now, we have to keep doing it, and then once we are out of bounds for T, then we return, then we check the index of the pointer of S. If that's also out of bounds, then we're good. Otherwise, that means that they're not subsequents of each other. So what we're going to do is we're going to like this. We're going to have 2 pointers, one starting at the beginning of S, one starting at the beginning of T. Each pointer will move to the right of each string, and we'll just be comparing the characters. If they're the same at a particular pointer, we move them both to the right. If they're not the same, then we just move the one for T to the right. That's how we make sure we get the the relative order to be the same. So when you do this, we have I is equal to 0, J is equal to 0, right? So while J is less than length of T, right? So now we check if T of J is equal to S of I, right? J plus equal to 1, I plus equal to 1. Otherwise, we just simply move J plus equal to 1. So we can just do this. In all cases, we're moving J, right? So yeah. Now let's say we looked at every character in T. Now we check if return I less than the length of S. T of j is equal to s of I. Okay, I plus equal to what? And I can know. Oh, sorry. If it's less than or equal to this, just need to prove that it false. A. Oh, sorry. You have to do this. You have to check if it's greater than or equal to the length of S. Yeah. That should be everything. Oh, what if you have an empty one, right? Yeah. Well, in that case, we can just have a base case of if length of S is equal to 0. That's going to return true all the time. Because if empty is always a sequence of yeah, and empty is also always a subsequence of some other string. Oh, okay. Right, you are doing, yeah, we are looking at, so there could be the case that where, we finished looking at S before we finished looking at T, right? Then even that's fine. So while I is less than length of S, yeah, that should do it. That's that also for paper this. Yeah, you have to be careful with your indices because in this case what we're doing is we're looking at two strings, right? But we're moving both of their indices forward, and we need to check both things that But whenever we're done looking at one of the strings, we need to check that have we looked at all the characters in S? If we have, then we're in a good position, and it's a subsequence. Otherwise, it's not.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve a problem, is subsequence. So subsequences come up a lot, especially in dynamic programming problems. So this is a good question to kind of get familiar with them before you solve some of those harder dynamic programming problems. Problems like longest common subsequence, which is a problem that I'm probably going to be solving pretty soon, probably in the next video. So we're basically given two strings, right? S and T, and we just want to know if S happens to be a subsequence of the string T. So first you have to understand what a subsequence is. To say that S is a subsequence of T basically means that all the characters from S, so let's say that this was our string S, all the characters of S can be found in T, right? Let's say this is our T string. All of the strings from S can be found in T in the order that they're given. So ACE, right? ACE can be found in this string with eliminating some characters. So you take the A, you can find it in the first position. You take the C, you can find it in the third position. And you take the E, you can find that in the last position, right? We're not required to use every character. So basically what we're doing is getting rid of the B and getting rid of the D, and then you can see that this string becomes ACE, right? So therefore ACE is a subsequence of T. Take a look at this. If this was our string S, it would not be a subsequence. Even though the characters can be found, right? A, E, C can be found, they're not in the order that they need to be in, right? So it seems like a pretty straightforward problem, and that's because it actually is. That's why it's an easy problem. So we can actually do this with a linear time algorithm, basically by comparing the two strings. So I'm going to show you how to do that right now. So the first example returns true because S is a subsequence of T, but how can we determine that? How can we prove that that's true? So it's actually easier than you might think. We're going to use 2 pointers. So I'm going to have one pointer I initialized at the beginning of our string S, and I'm going to have another pointer J initialized at the beginning of string T, right? And really, we're just checking all of these characters. We want to check them off. We want to say, okay, A can be found in T, B can be found in T, and C can be found in T, right? And if we have some extra characters like these, it's okay. We're allowed to skip those characters. So when we're using our pointer J, we're allowed to skip some characters, right? But we want to, with our string S, we really need to know that every one of these characters can be found here. So it's a 2-pointer solution, right? We initialize our pointers. Let's compare. Are these 2 characters equal? Yes, exactly they are. They're both A. That's what we wanted. We needed to find an A. So now that we found that A, we can shift our I pointer to the next position. We're going to be looking for the next character B. We also have to shift our J pointer because we're not allowed to reuse this character, right? So we shift our J pointer over here. And now we're looking for B, so compare B with H. So this is H, right? That's not B, that's not what we're looking for. So since we didn't find this character, we can't shift our I pointer. But we do have to shift our J pointer because this is not the character we're looking for. We have to check the next character. Now let's compare the characters. B equals B, great. So we found the character. We know that when we find the character, we actually shift both of the pointers. So let's shift our I and let's shift our J pointer. And now the only character we need to find is C. So we look at G, it's not C. So in this case, when we don't find the character we're looking for, then we only shift our J pointer, right? So J is D what we're looking for. It's not equal to C, so we shift our J pointer again. So now J is over here. That's the character we're looking for. We found C, so we shift our I pointer once more. Once I is out of bounds, that means we found every single character we were looking for, right? And we can check every one of those characters off. That means we found our solution. So that means we can stop the algorithm and return true. So CJ, it doesn't really matter where J is or what it's doing. Once I reaches out of bounds, we are done. So we return true. So now let's look at the second example. How do we know if that S is not a subsequence of T? Basically, how do we know when we need to return false? So we're going to run the algorithm exactly as we just did. So we're going to initialize I and J just as we did. So now we want to find this A, right? The first character. So we compare it. Yes, we found it. So when we find the character, we shift both of the pointers, right? So I and J are at the next position. So now we're looking for X, but you're going to see we don't have an X in the other string. So let's look at this position. H, that's not X, right? So we shift our J. B, that's not X. So we shift J again. G, that's not X either. So we have to keep shifting J, right? We shift it here. That's not it. We shift it here. That's not it either. So now we've gotten to a point where J is out of bounds, right? We have no more characters to check, but we still need to find these 2 characters, right? We need to find X and C in that order, but we didn't find them. So what this means is we have to return false. S is not a subsequence of T, right? So we return false. That's how you know you return false, if J is out of bounds before we find every character we need to. And clearly you can tell that this is an O of N algorithm where N is basically the total number of characters we're given in S and T, so S plus T basically. So with that being said, let me show you the code. So as we showed, our I and J pointers are both is equal.
Yeah, exactly like what I had. Yeah. So this time complex is O of N, and you have to be careful with your conditions, like your conditions in your while statement, that you have all the ones that you need, especially when you're using indices and strings or arrays. You want to make sure you don't go out of bounds, and that index is actually valid. Length of last word given string S consisting of words and spaces. Return the length of the last word in the string. Length of the last word. A word is a maximal substring consisting of non-space characters only. Okay, so in this case, hello world, and the last word is world, and in the second one, the last word is moon. Again, we want to get the last element right from the right side. So we'll start off at the very end of the string, the right side, and we'll go backwards, and then we'll keep going backwards until we see a non-space. The moment we see a non-space character, we'll increase our counter until we see a space. So for this, we can have some kind of flag, and then the moment we see the space, we return whatever the character is, or whatever the count is. Yes, let's have an index, ID x, which is equal to length of s minus 1, okay? And then a flag can be is, a last word found. Initial will be false. While ID x is greater than or equal to 0, check if the last word has been found, and we also want to have okay, if the last word has been found, right? What we're gonna do is we're gonna go and check if the last word found, and if s of ID x is not equal to space. So let's see, we don't check one thing. So s consists of English started with spaces. Okay, that's fine. And it's not like any character, just simple. There will be at least one word in s. Okay. Okay. Okay.
I know the mission is same. I made a splash, now all of my passes last like running a race with Usain. I keep it coming like.
Let's see if you find the last word, and the, but let's see. L if s of is equal to, right? Return output. IDX plus equal to 1. Okay. So yeah, if let's say we haven't found the last word, right? That means we've just encountered a space. We just keep moving the index down by 1. And let's say we do find the last, now we want to have, LF s of IDX is not equal to, right? It's not a space. True. Okay. Right. And then we just want to return. So we start off at the very end, right? We check, okay, have we found the last word? We have not, right? So no. No, mine is sorry. So yeah, if we have found the last word, first we check, have we found the last word? Right? Let's say we have not found the last word. What we do is we keep moving the index down. Let's say now we do find the last word, right? Last word. And let's say now let's say we do find the last word. We'll come with this case, right? This condition. We'll set the last word found as equal to true, and then we'll increase the output by 1 because we're seeing the first character of the last word. Then we go back here. Then we reduce index by 1. We found last word, and is the current character that we're honoring that is that not equal to space? If it's not, we keep doing this. Yeah, and then if we do reach a space, we just return output. There is at least one, right? So we still need this. Or we can just do that would be fine. index is greater than 0. Last word was not found. False. False. Come here. SFN is not equal to this. True. Now last word found is set to true in this case. And now we're here. Okay? And it's not equal to this. Oh, I know. Yeah. So what we want to do is we want to check last word found. Okay. Okay, well, index is this, right? What we do is we go, okay. Let's have this in the very top. So, if we find the last word and we see a space, then we just break, okay? Now, okay, so now we go to check. If we found the last word, and this guy is, right, okay, so now all we do is this. Let's do it again. So let's say if we have found the last word, and we reach an empty, we just break. Otherwise, what we do is, okay, anytime we see a non-space, we set last word found to be true and increase the output by 1. So in this case, what I'll do is, okay, 1, 2, 3, 4, 5, and then when you reach here, and when you see a space, this guy right here, it'll just break. In the case of something like this, what it'll do is, it'll
You heard of this new tool? It's Creatify, and you can literally create TikTok ad videos without having to film them yourself. These videos are full.
Yeah, it's just stupid conditions, like I said. So yeah, it's really nice to set your base case, I guess, first, or not base case, but your condition that helps you break out of your for loop or your while loop in this case. Yeah, and then all you have to do is once you set that, right, then you check, okay, if I don't see space, if I don't see a space, it's increase the counter by 1. But let's say the moment I see a space, and I have found that last word, then yeah.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's go a little easy on ourselves and solve the problem length of last word. If you're a beginner, I would recommend solving this problem, and maybe you can try solving it by yourself and then compare your solution with mine later in the video. We are given a string S consisting of some words, and these words are separated by some spaces. Among all of these words in the input string, we just want to return what is the length of the last word that occurs in the string, and we're guaranteed that there's going to be at least one word inside of the string. So let's take a look at an example. The first example, we have the first word hello separated with a single space from the next word world. And then that's kind of the end of the string. So what's the length of the last word? Well, the last word is here, world. Its length is 5, so we can return 5. The second example is a little bit more interesting. So in this case, we have some leading spaces, multiple leading spaces. We have a word, then another space, another word, and then a few extra spaces, another word, a few extra spaces again, another word, one space, and then this is actually the last word, but even after the last word, there are some extra spaces. So in this case, moon's the last word, its length is 4, so we can return 4. This is about as interesting of an example as we can really come up with. There won't be any, other edge cases for this problem, right? All we could be given is a string with some spaces in it, right? So there's many ways to solve this problem. You can kind of just iterate character by character. Every time we get a space, just ignore it. Every time we get a character, keep track of whatever the length of the current word is. So for example, we see the first character F, that's 1. The next character L, so then the length is 2. The third character Y, so the length is 3, and then we get to a space. When we get to a space, we basically want to reset the length because the next word, is going to start back at 0. So we'll reset this back to 0, get to the next character M, increment this by 1. The second character E, set this to 2, and then again have a space, so reset it back to 0, and then kind of just iterate through that, and then whatever the length of the last word was, we could end up returning that. A slightly easier way you might think of is, why do we even have to start at the beginning anyway? Why iterate through the entire array? It's kind of a waste of time. Why not actually just start at the end and then get the length of the first word starting from the end? And that's kind of how I'm going to do it. It's more efficient, and I think it's a little bit easier to code. So what we're going to be doing is, since we could have some leading white spaces, right? The first phase of the algorithm is just going to be eliminating these leading white spaces, right? So every time, so basically while we see a space character,
Yeah, you don't even like, I think you need a flag, because all you can do is start up, like, yeah, all you can do is just go like while s of idx is equal to space, and all you do is you go idx minus equal to 1, right? So this will first get rid of any leading spaces from the right side. Once you have that taken care of, right? So now you'll pop out when you see a non-space thing, and then what you can do is, and then all you do is while s of idx is not equal to this, okay, and then you just, break, right? Either way, if let's say you just have one word in there, right? You would still, this would still work for that, because what you're going to first, this one going to be left, there's no leading space, and there's just one word. Right, let's say it's just the word moon there. You would come to this condition, or this second for loop. Well, s of index is not equal to space, so you go 1, 2, 3, 4, and then you keep idx minus equal to 1, right? And then all you do is you just return output. Yeah, that should work as well. But you don't really need flags or anything like that. Index out of range. While, right, you always want to have the condition to make sure that you're still staying within your like appropriate indices. Yeah. That'll work. Always have this, even if you have like a loop within a loop, you should always have this. And then you don't really need this. You just have your output, and that should take care of everything for you. Yeah.
we're going to increment our pointer I, and then keep shifting it until we finally get to the non-space character. In this case, that's going to be at this word N. And then the second phase of the algorithm is basically going to be counting how many consecutive characters that we see before we either reach the end of the string or before we reach a space character. So basically increment the length until we see a space or reach the end of the string. In this case, we'll see N, O, O, M. Our length will be 4. Then we'll see a space character and then exit our while loop. So then the second phase of the algorithm will be completed and we have the result that we want to return, and then we can go ahead and return that result. Now, the time complexity, we might potentially have to iterate through the entire string if we have, just a single word in the string. So the time complexity is going to be big O of N. There's no extra memory needed. Yes, we have a variable that's keeping track of the length, but it's just a single variable, nothing more. So the memory complexity is big O of 1. So that's the solution we're going to be coding. So let's jump into that now. Okay, that's not super easy problem, as you can.
Okay, yeah, so kind of similar to what I had. Instead of having, yeah, so like what you did was you have this, you keep doing this, and then they had this on the outside, right? Yeah. Yes. Oh wait, sorry. is a little bit, I guess it's a little bit cleaner because you don't have like loops and loops, but it does the same thing. Yeah. Oh, we got a chat. I'm a fan. Thank you for being a fan. I hope you're enjoying this. Let's go on to the next question. That's 2-7. Okay. Okay, so 2-7. Given an array of integers nums and an integer target, return the indices I and j such that nums I plus nums j equals to target. So okay, you can assume that every input has exactly one pair of indices that satisfy this condition. Let's look at nums length is between 2 and 1000. Okay. This. So one thing I guess is, you can have a for loop, right, that loops through this array, and then have a second for loop that loops through, the I plus 1 element to the very end. And then you just, sum, you have 2 for loops, and then you sum each, you do sums, right? And then you see if you reach target, you return, but that is time complexity of full n squared, where n is the length of nums. Can we do this in all of n? So if I start at 3, how much do I, so essentially what we're doing is when we have 2 for loops, let's say we have 2 for loops, right? We start with 3, okay. So we got 3 plus 4, 3 plus 5, 3 plus 6, right? Well, in this case, 3 plus 4 gives us 7, but let's say the 4 was at the very end, right? The 3 plus 5, 3 plus 6, and then we check 3 plus 4. And then we do is we check 4 plus 5, 4 plus 6, 4 plus, so on and so forth. So, can we reduce the amount of work that we're doing here? To reduce the amount of work, because what we're doing is, we're doing 3 plus 4, then we're doing 3 plus 5, and 3 plus 6, and then we're doing 4 plus 5, right? One thing we can track is, okay, we can keep track, okay, for 3 to reach 7, we need a 4, okay? For 4 to reach a 7, we need a 3. For 5 to reach a 7, we need a 2. For 6 to reach a 7, we need a 1. Now, how can we see that, quickly see that, the thing that we need, do we have it or not? Of course we can, let's say we come here, right? To reach a 7, we need a 1. Do we have 1s here? No, we don't. To reach a 7, we need a 2. Do we have any 2s here? No. To reach a 7 here, we need a 3. Do we have 3? Yeah. So can we keep track of what we need? And we can use like a dictionary or a set, right? We just constantly look up. Because the index doesn't matter, we just want to see if something exists there, right? So we can do is we can say, okay, so for to reach 7, for 3 we need a 4. So we can have a dictionary where we have, okay, 4 and 3 give us a 7, right? So that when we reach here, 4, we check, does 4 exist in this dictionary? Yes, it does. If so, what do we need? We need a 3, so we get 4 and 3. So what instead we'll keep track of the indices, right? So that when we reach 4 here, we get the index 0, which is what we need, and we have the index 1 because we're looping through the array. So let's create a dictionary. We can call it this, right? For I in the range of nums. So this is equal to nums I. Now target, can it be more than nums? Target can be anything. Doesn't matter. Okay, so target minus nums is the diff, right? If diffs, diff, and I. Otherwise, if it's not there, right, what we do is we go diffs, diff will equal to I. And there is at least one like, pair that exists. So we don't have to do anything to that. What's wrong? Return. Let's see now. Return, yeah, you're returning the list. So it wasn't returning. Lock wasn't done. So 3. I need a 4. We don't have 4. Nums I is 4. Is 4. Parameters of the gift is equal to target minus nums I. Target is what we're looking for. Minus nums I. So 7 minus 3, 4. Is 4 in here? No, it's not. So we take this, we add diff, which is 4. Then we set I, which is 0. Then we come here. Oh. Why are you looking at diff? You're not supposed to look at diff. You're supposed to look at nums I, right? You have to look at if the current element that you're on right now, is that present? Is that, you know, the difference of something you've seen in the past? Yeah. Oh, sorry, yeah, nums I. That's true. And in terms of time complexity, it's O of n, where n is the length of nums. Space complexity is O of n because you could potentially be storing every element in nums. The difference of every element in nums. So yeah, look at the solution.
Let's solve LeetCode 1 two-sum, the most popular LeetCode question. So we're given an input array and some target, in this case 9. And we want to find the two values in this input array that sum to 9. So in this case, it's 2 and 7. Now we want to return the indices of these two values. So the index of 2 is 0, the index of 7 is 1. So we return 0 and 1. We're guaranteed that there's exactly one solution, so we don't have to worry about not finding a solution, and we don't have to worry about multiple solutions. Now the most intuitive way to solve this problem is basically just check every combination of two values and see if they can sum up to our target. So we start at 2, we check every combination we can make that includes 2. So we scan through the remainder of the array 1, 5, 3 and check if any of those numbers added to 2 sums to our target 4. In this case, none of them do. So next we can repeat the process. Let's check every combination including 1 that sums up to target 4. So we scan through every element that comes after it, 5 and 3, and we find that 1 added with 3 sums up to our target 4. Notice that we didn't have to check the values that came before 1 because we already checked the combination 2 and 1 when we were up over here. Remember when we checked every combination with 2? So we didn't have to repeat that work down here. We only had to check the numbers that came after 1. So the runtime of this algorithm isn't super efficient. This is basically brute force. We're going through the entire array of length n, and we're going to do that worst case n times for each number. This means that the overall worst case time complexity will be O of n squared. So can we do better? Now the thing to notice is that for each number, for example 1, the value we're looking for is the difference between the target and this value 1. So we're looking for 4 minus 1, which is equal to 3. So that means this is the only value we can add to 1 that'll equal the target. So we don't have to check every number, we just want to know if 3 exists. Now the easiest way we can do this, the most efficient, is by making a hash map of every value in our input array so we can instantly check if the value 3 exists. Now let's try the same problem, except let's use a hash map this time. Now in our hash map, we're going to be mapping each value to the index of each value. So the index of 2 is 0, the index of 1 is 1, the index of 5 is 2, the index of 3 is 3. So in our hash map, we're going to be mapping the value to the index. Now we could add every value in this array into the hash map before we start iterating through it, but there's actually an easier way to do it. If we added the entire array into the hash map initially, then we would get to the value 2 first, right? We would want to check, does the difference between target 4 minus this value 2, which is equal to 2, exists in our hash map. And we would find that 2 does exist in our hash map, but we're not allowed to reuse the same one, right? Because they're both at the same index. We can't use the same value twice, so we would have to compare the index of our current 2 with the index of the 2 that's in our hash map. There's actually an easier way to do this though, and it's a little clever, and let me show you how to do it that way. So doing it this clever way, initially we say our hash map is empty. So we get to the value 2 first of all, right? And we want to look for the difference 4 minus 2 in our hash map. Our hash map is empty, so we don't find 2. So then after we've visited this element, then we can add it to our hash map. So now that I'm done visiting it, I'm going to move to the second element 1. And before I do that, I'm going to add this value 2 to our hash map, and the index of this value is going to be 0. Now I'm at 1. I'm looking for 4 minus 1, which is 3. I see 3 isn't in our hash map, but it actually is in our array. So what's the problem? Well, for now, we're going to say we don't find a 3. So we add 1 to our hash map. The index of this 1 is 1. And now we move to the next element, 5. We check, does 4 minus 5 exist in our hash map? That's -1, so no, it does not. Then we add this 5 to our hash map and its index, which is 2. And we move to the last value in the array, 3. We check, does 4 minus 3 exist in our hash map? Now that's 1, so we see it does exist, right? Right over here. The value exists and its index is 1. So now we found our 2 values that sum to the target. And we want to return their indices, which are going to be 1 and 3. So with this algorithm, we don't have to initialize our hash map. It can be initially empty, and then we can just iterate through this array in one pass. Now, the reason the algorithm can work in that way with just one pass is this. So let's say we had a giant array, right? We know for sure that there are 2 elements in this array that sum to our target, right? We don't know where they are. They're at some arbitrary location. When we visit the first one of those elements, our hash map is only going to be this portion of the array. It's only going to have the values that came before the first value. So we're going to notice that the second value that can sum to the target is not going to be in our hash map yet. But once we get to the second value, our hash map is going to be this portion. So every value that comes before this, right? So we're going to be guaranteed that once we visit the second element that sums up to the target, we're going to be guaranteed that the first one is already in our hash map, so we're guaranteed to find the solution. Now, since we only have to iterate through the array once, and we're adding each value to our hash map, which is a constant time operation, and we're checking if a value exists in our hash map, which is also a constant time operation, the time complexity is going to be big O of n. We are using extra memory, right? That hash map isn't free, so the memory complexity is also going to be O of n because we could potentially add every value to the hash map. So now let's code the solution.
this particular number in this array does it exist, and it's not the same index as what I'm on, and return it, or you can just do it in one pass like that. I guess one is you can also sort it, I guess. Let's do a little complicated. Yeah, I would say just ignore the sorting one, because it's high time complexity, and still giving the same space complexity.
Calgary has this emerging tech industry and tech community.
We're destigmatizing mental health.
We've made a blood test to detect breast cancer.
Okay, Latifa, I'm going back in, okay? Yes, I do. Just like tell me when the chai is ready, or bring it here. Okay? Just don't say anything crazy. Okay.
Let's continue. Longest common prefix. Write a function to find the longest common prefix string among an array of strings. If there is one prefix, return an empty string. So longest common prefix. Okay. Okay. So. Okay, so one way that I can think of doing this is compare the ith string and the I plus 1. Okay. Compare the first letter, move on second letter, move on third letter, until you don't see something that's equal. Or you go past 1. You want the longest common prefix, right? Compare F and F, compare O and O, W and W. It's 4. And then I compare this and this. Compare F and F, L and F, O and O. And then we're done, so still 4. But then okay, look, so the longest common prefix, I don't have to compare I and I plus 1, right? I can just compare the first one with all, yeah, because I want the longest common prefix, correct? Yeah, so longest common prefix, which means it has to be common in all of them. Yeah, so I can just compare the first character, or the first word in the string with all the other ones. Yeah, so. Let's do this. And I need the longest common prefix, right? Yeah. again, a common mistake is, you don't update your index. So you don't want to do that. Oh, wait, sorry. Should have the question a little bit better. You're supposed to return the string, not this. Okay. I'm going to just call this common prefix. Okay. Okay.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem longest common prefix. We're given a list of strings, and among all of these strings we want to return whatever is the longest common prefix. Now what is a prefix? Well, it's just a portion of the string. So for example, this string flight, a prefix is just any portion of the string starting from the beginning. So F is a prefix, FL is a prefix, FLI is a prefix, flight itself, the string itself, is a prefix. As long as it starts from the beginning and is continuous, then it's a prefix. And we want to return the longest common prefix among all of these strings. So, what's the intuitive way to tackle this problem? Well, look at the beginning, right? All three of these strings start with an F, right? So F is a common prefix among all of these strings. Let's look at the next character, L. L is the second character in all of the strings. So another prefix that's common among all the strings is FL. Now let's look at the third character. O is the third character in this string. O is the third character in this string. And I is the third character in this string. So unfortunately, FLO is not common to all three of the strings. It's common to these two, but it's not common to this one. So FL is going to be the longest common prefix that we have, so that's what we can return. So the problem really is that simple, but there are a couple edge cases that can trip you up if you are a beginner. So we're going to be focusing on that, especially when we code it up. So basically, we are going to simultaneously iterate through all of the strings that we're given. One of the strings could be shorter than the other string. So for example, if we weren't even looking at this string, we can see that these two strings, this string and this string, they both start with flow, right? So flow is a common prefix to both of these two strings. Then if we got to the fifth character, we'd see that, okay, E is the fifth character here. This string does not even have a fifth character, right? So if we get out of bounds out of one of the strings, then we know we can stop, right? And that makes sense, right? Flow would be the longest common prefix among these two strings. So what's going to be the time complexity of this solution? Well, potentially we're going to have to go through every single character of every single string. That would basically be the case if, we had, let's say we had flower and we had it multiple times, right? Then we'd have to potentially iterate through each of those flower strings, right? Because they're common, so we wouldn't stop. And then we have to go through every single character. So the overall time complexity, let's say, is going to be n, where n is the total number of characters that we're given. Or if you want to say that n is the average size of the string, and we have m different strings, then you could say this is the time complexity, right? However you want to formulate it. But overall, we're going to just have to iterate through each character in the entire input once. With that said, we're ready to code it up. So the first thing we're going to do is initialize our result. Remember, if let's say we didn't even have a common prefix among any of the strings, right? They all started with a different character. Like we had A, we had B, we had C, right? There's no common prefix among these three characters, so then we just return an empty string because there is no common prefix. So we initialize our result. Then we want to simultaneously iterate through all of the strings, right? So we're going to use a pointer I to indicate what index that we're at in the strings. And we're gonna go through, let's say, through every single character of, let's say, the first string, right? I'm just putting the first string here, strings at index 0. This is just the first string. I'm using that arbitrarily, right? Because it could be possible that this string is not the shortest string in the input, right? In which case we'd want to stop this for loop earlier than it's actually shown right now. So we'll have to remember to handle that case. I'll handle it slightly differently than using a conditional out here. So, okay, so we're iterating through every index. We want to now iterate through every single string and make sure all of the strings have the exact same character at index I. So let's go through every single string. So for S in the list of strings that we're given, we want to check that every single string at index I is the same. So let's compare this arbitrary string S to the first character of the first string, right? We could pick any of them, but we just want to make sure that they're all the same. So we'll just make sure to choose the same one every time. So we'll go to the first string, right? Strings at index 0 is the first string in the input, and then we'll go to index I of that string. So as long as they're equal, we're going to continue. If they're not equal, though, which is this case, then we're going to have to return. right? We're going to have to return whatever our result is so far, because we know that whatever this prefix is, that's going to be the result, because we can't make the longest common prefix any longer. But there's one case that we didn't think about. What if we went out of bounds, right? What if this string S is out of bounds? Because we know this is going to be in bounds because that's our I pointer up above, right? I is always going to be in bounds of the first string because that's what we're iterating through up over here. But this string might go out of bounds. So before we check this condition, we're going to make sure that I is in bounds. So we're going to say that if I is equal to length of S, which means it's out of bounds, right? Then we're going to also return, right? We're not even going to check this line of code. If this evaluates to true, we'll immediately return. That's how Python works with the conditionals. If the first one is true, we don't even check the second one. And so that is the entire logic of the for loop. But remember, every time we go through a character, we want to add it to our result. So we can do that pretty easily like this. We can go ahead and add that character that is common among all the strings to our result. And then once we're done with all of that, we can go ahead and return the output result and
word in the list. Okay, and that might be better because you can